Hello there, welcome to the new lecture. After the end of this tutorial, you would be able to perform fan selection. So let's start. Fan selection. There are many factors to consider while selecting a fan. So first we'll understand how a fan model can be selected. As we know, all fans perform the basic function of moving air from one space to another. Due to variety of applications, different models are manufactured. The selection of suitable fan from various available models is very important. Now this depends upon the on-site location, condition, the total pressure losses and so on. So suitably a fan will be selected which will circulate the air from the central air handling units to the conditioned space. As far as fan models are concerned, they can be direct drive models or belt drive models. This is how direct drive fan looks and belt drive fan looks. Here the motor shaft is directly connected to the fan and over here it is connected with the help of a belt. So the position of motor and the fan is at some offset position. Direct drive fans are used wherever it is required to move air 2000 cfm or less. And the static pressure they can overcome is up to 0.5 inches of water column. They are used with speed control to adjust the CFM, so CFM can also be adjusted in such models. However, belt drive fans are used wherever the amount of air to be moved has the value above 2000 CFM. And in such cases, the static pressure to overcome is more than 0.5 inches of water column. So this value 0.5 inches of water column and 2000 CFM will determine either of direct drive or belt drive fans will be used. Now belt drive fans also have adjustable pulleys. They can be having different sizes which will regulate the speed of the fan, and CFM can also be adjusted by a factor of 25%. Now wherever high temperature fans are required to move air above 50 degrees centigrade or 122 degrees Fahrenheit, belt drive fans are always recommended. Now as we know, fans can be axial or centrifugal. So an axial fan that flows the air axially, the centrifugal fans that move the air at some angle, the propeller fans or the axial fans are used is 5000 cfm or more, and the static pressure they can overcome is up to 0.5 inches of water column. Now they have the limit of temperature up to which they can operate, and that is 40 degrees centigrade. The centrifugal fans can also move 5000 cfm or more, and the static pressure they can overcome is 0.5 inches of water column or more. So if there is a choice between axial fan and centrifugal fan to move air above 5000 cfm, either of them can be used. But if it is required to have static pressure overcome above 0.5 inches of water column, then centrifugal fans are used. Centrifugal fans produce less noise, and they can also operate up to a maximum temperature of 40 degrees centigrade. Now fan models can also be decided on the basis of fan location. There are three common locations to mount. First, on the roof. So these are fans that are installed on the roofs. They can also be installed on the wall. They can also be installed in ducts. To properly select a fan depending upon its location, it is important to survey the building structure so that best location of fan can be chosen. In all of these configurations, basic components such as blades remains the same. However, it is only the outer casing that changes. Another factor to consider while selecting fan is the amount of airflow that the fan is required to move, that is the volume flow rate measured in CFM. Once the fan type is decided based on the model, the amount of air exchange can be determined, and we can use this simple formula to find the amount of air that a fan requires to move. The formula says CFM equals to the room volume divided by minutes per change, Minutes per change is an important term and we'll understand this in detail over here. Let's say minutes per change for any given case is 5. This means in 5 minutes, the entire air occupied inside the room will be changed. In the same way, if we say minutes per change is 10, this means 10 minutes per change, which means every 10 minutes, the total volume of air inside the occupied space will be replaced. This is done in order to maintain proper ventilation and maintain quality of air inside the room. The room volume can be found by using this simple formula of cuboid, which says length into width into height, which is basically the product of all the three dimensions. Then to find minutes per change value, we can refer to this table. Here different areas are mentioned. They can be assembly hall, attic, auditorium and so on. And same over here, they can be mills, office spaces, packing houses. Now based on these different facilities, proper value of minutes per change can be selected. So let's say for assembly hall, we can select any value between 3 and 10. So let's say if we select 5, this means for an assembly hall, every 5 minutes, the entire amount of air inside the room is supposed to be changed by fresh air. Now we'll do a sample problem in order to understand this in more detail. So it is mentioned that there is a building which requires an exhaust fan to ventilate a general office. The office measures 30 feet by 40 feet by 8 feet. The office is generally crowded. Determine the CFM. So under this situation, what should be the airflow required in order to have proper ventilation, and accordingly fan can be selected. So we'll determine the CFM in this case. To do that, first we'll calculate the room volume. Since all the three dimensions are given, we can multiply them to find the volume of the room in cubic feet. Then to find the volume of minutes per change, we refer to this table because we are talking about office. So we'll select the column of office. Here we see that the value is given anywhere between 2 and 8. Since it is mentioned that the office is generally crowded, so we'll take a suitable value of minutes per change, that is 4. And now by using this main formula, we can find the CFM requirement for this situation to be 2400 cubic feet per minute. So now a fan is required that can move 2400 cubic feet of air every minute. Now there's a very important concept of minutes per change, and there is another term which is used in relation to this is ACH, which stands for air changes per hour. There's a very big confusion in the industry related to this. You can try to do a simple observation. Just ask the same question to 10 people and analyze their response. This will let you know how deep the concept is. So what is ACH? ACH means air changes per hour. This means how many times the total volume of air inside a room will be changed every hour. If we say the value of ACH is 5, this means in 1 hour, 5 times the total amount of air inside a room is supposed to be replaced by fresh air. In the same way, if we say the ACH value is 20, then in 1 hour, 20 times the total amount of air inside a room is supposed to be changed. Now this looks very similar to minutes per change. However, they are different quantities. Minutes per change means in how many minutes the total amount of air inside the room will be changed. However, ACH means how many times the total air inside a room will be changed in 1 hour. So if we have the table of minutes per change, so we'll use this formula and determine the CFM. However, if we have the ACH table, which is also widely used in the industry, so we'll refer to the ACH table and use this formula instead of this one. If we have the table for ACH, we can use this value and accordingly calculate the CFM. So it's really important to understand the difference between these two formulas. They are used along with their tables. Fan manufacturers sometimes provide the table of minutes per change. In that case, we'll use that table and this formula. However, if you have a table of ACH, there the value of ACH will be mentioned obviously, and from there you can find the value and use in this equation to determine the CFM. Now this is a formula that relates these two quantities. If you know ACH, by using this formula you can calculate minutes per change, and if you have minutes per change you can calculate ACH. So let's say you have a table of minutes per change, but you don't know this formula, you only know this formula. So if you have the table of minutes per change, you can take the value of minutes per change and use in this equation and find the value of ACH. Now this value of ACH you can use in this formula. The results are going to be same. Again, I'll repeat since the concept is very important. The table of minutes per change is provided by fan manufacturers, and if you have that, you will be using this formula. And if you have the value of ACH, then this formula will be used. Alright, moving forward, static pressure built up inside the ducts. This is the amount of static pressure that the fan must overcome, and this depends upon the air velocity in the ductwork. So let's say this is a duct. First we have to consider the number of turns. Here we see that the number of turns are 2. Then we'll also consider the duct length, which is the total length from starting to end. Other factors to be considered are the elements or the accessories used in duct installation, such as grills, elbows, dampers, and so on. So all these factors will be considered in order to determine the static pressure, and once the value of total static pressure is found, suitable fan can be selected which would be able to overcome the total static pressure built up by the ductwork and the resistive elements or accessories associated with the ductwork. Now we'll refer to this table. This gives us direct values of some factors. So to determine static pressure, some guidelines are used. For non-ducted system, we use the value of the resistance as 0.05 inches to 0.20 inches. So this value of static pressure can be used for non-ducted systems. For ducted systems, however, we can use the value from 0.20 to 0.40 per 100 feet of duct length. These values are specified by the manufacturers, so it is always advisable to use the accurate values provided in the fan catalog. Now for fittings, also these values are provided by the fan manufacturers. Generally, we'll be taking the value as 0.08 inches per fitting. So following these guidelines, we'll now do a sample problem to understand more about this concept. So first, we'll find the total static pressure drop for given situation. So what's the situation? Here we have a duct. Its horizontal length is 6 feet, vertical length is 4 feet. There is a grill and there is a damper at the outlet. Here the airflow is from a restaurant, and here the air flows from the exhaust fan to the atmosphere. So this is the overall situation. Now we need to find the total static pressure drop in this simple situation. So referring to the static pressure chart above, we can assume for ductwork 0.20 inches to 0.4 inches per 100 feet of duct length. So first we'll find the total duct length. So we'll assume any suitable value between 0.20 to 0.40. So we are now selecting 0.30 inches of water column static pressure drop for 100 feet length. Now for 1 feet, it is going to be 0.30 upon 100. Now we'll find the total length of the duct. So the total length of the duct is 10 feet, as can be seen. This length plus this length is 4, and from here to here it's 6. So total length of the duct is 10 feet. So for 1 feet, static pressure drop is 0.30 upon 100. So for 10 feet, the static pressure drop is going to be 0.03 inches of water column. Now for grills, which is located over here, we can use a direct value 0.08 as mentioned over here. We also have 2 turns, so for each turn we can take 0.08. So for 2 turns it's 0.16 inches of water column. And for damper, which is located over here near the exhaust, we can take a suitable value of 0.08 inches. So this is the static pressure offered by the individual elements. Now adding all these, we get the total static pressure loss to be 0.35 inches of water column. Keep in mind that the fan selected in this case must be able to overcome a static pressure value of 0.35 inches. Generally, some amount of factor of safety is considered, so it is advisable to select the fan close to 0.40 inches of water column static pressure. Alright, the next factor is sound power level. To understand this, we use the unit of zone. Now, zone is the industrial unit of sound pressure level. One zone, what does it mean? To get a feel of one zone, you can imagine you are inside an average acoustically room, and if you are standing 5 feet away from a refrigerator in a quiet room which is acoustically sealed at an average level, then the sound heard by you is going to have the intensity of one zone. So this is how one can understand the intensity of one zone. Few guidelines to follow in order to select suitable value of fan corresponding to the noise levels. So for different facilities, these are the recommended values as provided by AMCA. So for private homes, the range of zone has to lie anywhere between 1.3 and 4. A fan producing more than 4 zones should not be selected for private homes. In the same way, for conference rooms, the allowed value is 1.7 to 5 zones. So if there is a fan which is having zone level of more than 5, such fan cannot be selected for conference room, and so on. So this table will be referred while selecting fans as far as sound power level factors are needed to be considered. Okay, the last factor is the fan efficiency. Fan efficiency is closely related to the energy consumption of an air system. So if the efficiency is high, the energy consumption of that system is going to be low. Fans should be selected so that they can operate at high efficiency as much as possible. This will lead to better energy withdrawal and lesser operating cost. Now, there is an AMCA standard 20512 that provides fan efficiency grading, which is abbreviated as FEG. Now, this suggests a minimum value for fan selection. So, there is a minimum value of FEG as prescribed by AMCA in the standard 20512 that will be used to select fan on the basis of its efficiency. This is a chart where fan impeller diameter is mentioned on the horizontal axis, and here we have the peak total efficiency. Alright, now we have the fan efficiency grading values such as FEG 50, 53 and so on till 90. So these are regions or strips at different locations. Let's say we are talking about an efficiency grading of FEG 80. In this region, let's select any random position. Now, if we draw a line from here to the horizontal axis, the value is found as 25. And on drawing line towards the vertical axis, the value is found as 77. This means if there is a fan of FEG 80 with an impeller diameter of 25 inches, it will have an efficiency of 77%. In the same way, if we select another location in the same region, then we get the fan impeller diameter to be 15 inches and its corresponding efficiency is 73%. So let's say there is a situation where FEG 80 fan has to be selected. Now in this case there are two fans available, the one with 25-inch diameter and the other with 15-inch diameter. We can clearly see that from this chart we are going to select the fan with 25 inches diameter as it is having efficiency of 77%, which is more than the other fan of 15-inch diameter. So based on fan efficiency grading system, this is how fan selections are done. Now the fan selection range as prescribed in fan performance curves. This is the fan performance curve where we have CFM and pressure, and this is the fan curve. Now here we'll draw the total efficiency and total efficiency curve. For better economics, fan must operate near its peak efficiency. As we already know, the efficiency has to be maximum in order to have better economics or lower running cost. So this is the position of maximum efficiency. So we'll draw a line from here till the total efficiency axis. Now AMCA standard 205 recommends that all selections be made within 15 percentage points of the peak total efficiency. So this is the peak total efficiency. Close to this 15 points, we'll draw a line that will intersect the efficiency curve at 2 points, as can be seen in the chart. Now what next? From here, we need to draw a vertical line that intersects the CFM axis. As we can see that these lines also intersect with the fan performance curves at these locations. So these two locations will determine the selection range of any fan. So based on AMCA standard 205, now we can select a suitable fan close to 15 percentage point, and this is how the selection has to be done on the basis of fan performance curves. Okay, so now you can perform fan selection. Hope you enjoyed this session. See you back soon in the next one.